A clinical test on humans of a new drug is normally done in 3 phases. Phase 1 is conducted with a relatively small number of healthy volunteers. For example, a phase 1 test of a specific drug involved only 7 subjects. Assume that we want to treat 7 healthy humans with this new drug, and we have 15 suitable volunteers available. Let's complete parts A through C below. Now for part A, it says, if the subjects are selected and treated in sequence, so that the trial is discontinued if anyone displays adverse effects, how many different sequential arrangements are possible if 7 people are selected from the 15 that are available? Now we want to determine if the number of different sequential arrangements can be found using combinations or permutations. Since the subjects are distinct, no one subject can be chosen more than once, and the order in which the subjects are chosen matters. Use permutations to determine how many different sequential arrangements can be found. A situation using permutations when all the items are different must satisfy 3 requirements. First, there must be n different items available. Also, one must select r of the n items without replacement, and then finally rearrangements of the same items are counted as being different. Now, the number of permutations or sequences of r items selected from n different available items without replacement is given by the formula below. The factorial symbol denotes the product of decreasing positive whole numbers. So for example, 4 factorial is 4 times 3 times 2 times 1, which is equal to 24. And by special definition, 0 factorial is equal to 1. So here's our permutation formula, where we have n factorial divided by quantity n minus r factorial. So we know that n is equal to 15 and r is equal to 7. So we're going to plug that into our formula. So we're going to have 15 factorial divided by 15 minus 7 factorial. We'll always use the parentheses first. So 15 minus 7 factorial is 8 factorial. And then we have 15 times 14 times 13 times 12 times 10 times 11 times 10 times 9 times 8 factorial. So that means we can simplify the 8 factorial, and therefore we end up getting 15 times 14 times 13 times 12 times 11 times 10 times 9, which gives us 32,432,400. So therefore, there are 32,432,400 different sequential arrangements possible if 7 people are selected from the 15 that are available. So now let's take a look at part B. If 7 subjects are selected from the 15 that are available, and the 7 selected objects are all treated at the same time, how many different treatment groups are possible? Now, since the subjects are distinct, no one subject can be chosen more than once, and the order in which the subjects are chosen does not matter. So we're going to use combinations to determine how many different treatment groups are possible. So we're going to use the formula. N factorial over n minus r factorial times r factorial for combinations. Now with n is equal to 15 numbers available and r is equal to 7 numbers selected, find the number of combinations. So we have 15 factorial over 15 minus 7 factorial times 7 factorial. Well, we know that 15 minus 7 factorial is 8 factorial. And we know that in the numerator, we were going to go from 15 all the way to 8 factorial, so we can simplify that. And then 7 factorial we need to write out. 7 times 6 times 5 times 4 times 3 times 2 times 1. So we can simplify the 8 factorial. Okay, we know that 7 times 2, okay, gives us 14. Okay, we also know that 5 times 3 is going to give us 15. We know that 6 goes into 12 2 times. We know that 2 goes into 4 2 times. And we know that 2 goes into 10 5 times. So therefore, we're going to have the following. We have 13 times 11 times 5 times 9, and that gives us 6,435. So there are 6,435 different treatment groups possible. Now let's take a look at part C. If 7 subjects are randomly selected and treated at the same time, what is the probability of selecting the 7 youngest subjects? Now, to find the probability of selecting the 7 youngest subjects, we use the classical definition of probability. Assume that a given procedure has n different simple events and that each of those simple events has an equal chance of occurring. If event A can occur in s of those n ways, then the probability that A occurs is given by the following formula. The number of ways A occurs divided by the number of different simple events is s over n. Now we're going to let A be the event that a certain simple random sample is chosen. A can occur one way. Next, use the classical definition of probability to give the probability of selecting the 7 youngest subjects. Recall that there are 6,435 different treatment groups possible. So the probability of A is equal to 1 over 6,435. So therefore, the probability of selecting the 7 youngest subjects is 1 over 6,435.